Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will continue with more kinetics. We'll start with need for fixed second law and understand what is this second law and application of fixed laws to figure out various kinetic processes. This is basically to find a solution to a partial differential equation. These fixed laws are in that form with the right initial and boundary conditions. We'll see about them with an example. Then phase equilibria and diffusion. This is perhaps the most important things that we are trying to cover in kinetics, because whatever we are seeing till here is more about the fundamental laws of diffusion. And actually, when it comes to simulating, let's say, phase transformations, this is much more important, where we understand phase equilibria and diffusion together, where we will see whether as diffusion can be driven compared to random jumping. Then driving force and activation energy of a process. Then understand uphill diffusion, downhill diffusion. All these ideas are basically going to focus on how chemical potential gradient causes diffusion rather than the concentration gradient. And then diffusion that is driven, and for such a diffusion which is driven, we are going to use mobility. Mobility we will be using instead of diffusivity, it is much more useful. In the next class we will talk more about that. Let's see them one by one. Need for fixed second law. Fixed first law is this, but this can be used if the concentration profile is a straight line and does not change with time. Okay, if the concentration profile is a straight line, meaning the dc by dx is one value for all the locations, all the different x values, dc by dx is constant. Okay, if dc by dx is constant, then it is easy to apply fixed first law and get the flux, diffusivity and things like that. Such a diffusion is called steady state diffusion. Then we can use this directly, the fixed law directly, to understand the kinetics of such a process. But when that is not so, if the concentration profile is not a straight line and changes with time, okay, here it is straight line and does not change with time. Here it is not a straight line, some kind of a weird shape, and it is going to change with respect to time. Okay, and that is called as non-steady state diffusion, and it is difficult to understand the kinetics of it. That's where we need fixed second law. So let's start with fixed second law and see what is it. It's quite simple to understand. First start with this concentration profile is neither straight line nor stable with time. Okay, something like this. So here this is not a straight line, and imagine this is going to change with respect to time, something like this or something like this. It's going to change with the time. Okay, and here let's mark a couple of locations in the x-axis. This is basically the distance in the material itself. The concentration at this point x is this much, and x plus delta x is this much, and dc by dx is not a straight line. Okay, if this is the case, then how the flux will look versus distance, flux against distance curve, how it will look. When it is a straight line, how it looked, you can imagine how it would have looked. Dc by dx, if it is a straight line, then dc by dx is directly proportional to j. We just need diffusivity to understand that. If it is so, then if dc by dx is constant, then flux is going to be constant. Flux against distance will be a horizontal line. Okay, but in this case, when the concentration profile is not a straight line, then how it will look? If you see, flux at this point, because this is, if you draw a tangent here, you can get dc by dx here. That slope is steeper compared to a tangent to this point, right? Like this. So dc by dx is higher here and lower here. Therefore, flux will be higher here and lower here. Okay? So a higher flux for this point where x is marked, that location is marked as 1 here, and x plus delta x, this point is marked as 2 here, and here flux will be lesser because dc by dx is shallower here. Okay, so therefore different fluxes happen at two different locations. This is going to have consequences. If you bring the real material here and over this delta x distance between this point 1 and 2, you can see how is it. Okay, so this is the material. At this location, the flux is J1, which is higher, and at this location flux is J2, which is lower, meaning the amount of material entering this side is more, amount of material leaving this side is less. Therefore, over this delta x, there will be accumulation of material. As long as flux is different from one location to the next location, there will be accumulation of material there, right? Higher flux, lower flux. Therefore, accumulation of material happens. Therefore, this question comes, what is the concentration change or concentration increase in a small volume between 1 and 2 with time? Meaning, what is the concentration increase over time? This question is important when it comes to this kind of non-steady state diffusion. Somewhere the concentration is going to increase or decrease. What is the change in concentration over time? If we get this, basically we are talking about how the concentration profile will change with respect to time. If we capture that, we capture the kinetics. Okay. So how concentration will change with respect to time? That's the question. How concentration will change with respect to time is how the flux is varying over the distance. Okay. This is going to decide that. And when we write the flux JB at every location, we can see what is the JB based on at every location what is the tau C by dou x. So concentration gradient we can take from Fick's first law, we can calculate what is the flux at every location. So if this can happen, then we can put this equation and simplify it to this form. Dou CB by dou T is equal to diffusion coefficient multiplied by dou square CB by dou x square. Okay, distance is here, time is here. So this is Fick's second law. So if Fick's second law is available to us, can we predict the concentration profile, how it changes with respect to time? Answer is yes, we need to solve the Fick's second law and get this. Okay, Fick's second law of diffusion is there with us. How to get the concentration profile with time from this equation? Solve this partial differential equation. That's what we have to do with the right initial and boundary conditions. So what are we talking about as initial and boundary conditions? Initial conditions you can easily understand. Let's say Newton's laws tell you how material will move when the stress or force is applied. Okay. If the law is going to tell you that, let's say from some location, if some force is applied, the material will move in this manner. But if you want to know where exactly the material's location will be after different times, you need to know what was the first initial location of it, right? From there you start applying Fick's law. From there you start applying Newton's law, then it will move to, you can track the movement of the material. So initial condition is important to understand. The question that you ask is starting from an initial condition, knowing the behavior of the material from the equation, how it will evolve with time. Similarly, if some initial condition is there, for concentration, initial concentration profile is there, then with respect to time, how is it going to evolve? That we can understand based on Fick's second law. So what is boundary condition? I will explain that in the next slide with an example. Take this example. This is a solution of Fick's second law for the application of carburization. Carburization is an industry process where material is taken, let's say steel, and a carbon source is given at the surface. Therefore, continuously there is a carbon supply, and with respect to time, carbon diffuses into the steel, and at certain depth there will be some concentration for carbon. If that is achieved at certain depth, then the entire case above that, the surface above that, will have certain hardness. So it's a process to increase the hardness of the material. So if this carburization happens in the industry, the time to which carburization has to be done is an important question to ask, because that is going to affect the productivity, the distance to which carbon diffuses, so that enough carbon is present at certain depth to achieve certain hardness. So this is a very important question to answer, and Fick's laws can directly give us the answer. By solving the Fick's laws, we can get that. Okay. So how much time to do carburization till a certain depth achieves a certain concentration of carbon? That's the question. Okay. So how does concentration profile change with time? That's what fundamentally it means. What do we need to do for that? Solve Fick's second law and take the initial condition CS, carbon concentration in the surface is CS, and in the interior it is C0. See, what is the initial condition is this horizontal line here, C0, that is the concentration of carbon in the material. This is the material's thickness, 0 to x is basically into the material we are going, and from the surface to the interior, throughout the material carbon content is same when we start. And at the surface, what is the carbon concentration? Carbon concentration in the surface is CS, because very high carbon is available only at the surface. Okay. And with respect to time, you can see initially it is like a step profile. At the surface it is CS, then as the material starts the concentration drops to C0 and it is constant throughout. That is the initial starting time. Then with respect to time, this first curve is drawn. First curve tells you that carbon concentration is achieved, CS is achieved near the surface in the material, and from there onwards carbon content is slowly decreasing. Definitely carbon has diffused into this, but let's say this level here is the interest of us. This carbon level should be achieved at certain depth. Let's say this is the thickness of the material to which this level of carbon to be achieved. Then we have to keep drawing these concentration profiles after different time intervals. There is a particular time interval after which if you draw the curve, you will see that the location that you are looking for here would have achieved the concentration that is desired. Okay. So what we need to track is this concentration profile with respect to time. So this is what we need to track. Okay, what is boundary condition? Boundary condition here is quite obvious. You see, if the initial surface concentration is CS, and then if the diffusion starts and carbon supply is not there, it is only at the initial time the carbon supply is really high, and the moment diffusion starts, carbon supply is stopped, let's say. Then the concentration of carbon in the surface will start coming down. It's more like high concentration and low concentration, and everything becomes uniform, right? Carbon concentration here will start dropping. Okay, but in this particular example, we are saying that carbon is supplied from the surface. So continuously the concentration of carbon is maintained here at CS. Okay, so if the carbon content at the boundary is certain value and it is not going to change throughout the process, that is a boundary condition. We are imposing that. Okay, so that boundary condition and the initial concentration profile, if we take, that is initial condition, how the concentration will evolve with respect to time, we can track that. So these two conditions are important. So this surface condition, which is going to be CS always, is a boundary condition that is to be imposed. Okay, so this is why we have to solve Fick's second law with right initial and boundary condition to get the concentration profile with respect to time. Right. Now comes this important idea of phase equilibrium and diffusion. Let's start with this. We have seen this. There we have these 6 atoms, and a particular atom jumps from its location here to the next location. So this is the final state, this is the initial state. Between initial and final state, Gibbs energy is same, and in between it will go through activated state where it will go to a higher energy configuration. So the difference between the ground state and this excited state is the activation energy. Okay, so process coordinate is basically initial and final state is marked here. That's the process coordinate, right? So we have seen this. So in this case, Gibbs energy difference is not there. Jumping from left to right or right to left is going to be having same energy in the initial and final states. So initial and final states have same G. Now think about this. In this case, the initial state has this Gibbs energy, but the moment atom jumps to this location, it forms a very strong bond, let's say a high negative bond energy. If that happens, okay, in this scenario, bond energy is really low, means very strong bond is forming. If that happens, then Gibbs energy is favoring this configuration more. The Gibbs energy of this configuration is here. Okay, so much lower Gibbs energy is the final state Gibbs energy. If that happens, then there is a driving thing. This delta G A we saw, what is that? This delta G here is basically a driving force. Basically, from high Gibbs energy to low Gibbs energy, things are moving. We have seen such an extensive thermodynamics which tells that this kind of process is highly favored, right? So this jump, once it happens, the atom will come to a much lower Gibbs energy state, and think of the reversal. If this atom tries to go back to original location, is that jumping possible? It requires even higher activation energy now. This delta G and this delta Ga both become barrier for an atom to jump from here to here. Okay, so forward process occurs if delta Ga is available from here to here, but the reverse, if you think of it, let me put it in this manner. Okay, atom is here, and from here if it has to go back to this location here, this is the final state now, and if that has to happen, we get a very high delta Ga for the reverse process. Okay, so reverse process requires more delta Ga because the delta G, the driving force of the forward process, is added to it. Okay. So now we can compare these two things, driven versus random. Forward process is driven by reduction in G. We understood that. An atom jumping to a lower G position is unlikely to jump back to higher G position. Understandable. In this, diffusion is driven in the sense that atom, once it has the enough activation energy, it jumps. But once it jumps, it doesn't come back. This is in a sense driven, going from one place to the next place, right? So in this, diffusion is driven by this reduction in G, unlike the case of random jumping. Okay, random jumping is like this, right? From here to here or from here to here, there is no energy change. Atom can randomly jump. But here, when it jumps, it is stuck. And that idea can be applied to the entire material, not only for that one particular atom jumping. If if a system goes from one state to the other state, and if the Gibbs energy is lowered in that process, we call that Gibbs energy difference as driving force. And if it has a activation barrier to go from this state to this state, we call it activation energy. So now we are putting it for the entire process. Okay, so initial state, final state and activated states are there in the entire process. You can imagine based on the mechanism of this process, let's say this process of a material going from some high Gibbs energy to low Gibbs energy state, how it will move? It will move to these it will move between these states through diffusion. Diffusion is the process, and the diffusion process, the mechanism of this process itself has an activation barrier. That activation barrier is what manifests as the process, entire process activation barrier. Okay, and that's what we are putting here, driving force and activation energy. This picture is quite important to understand the kinetics. So keep this in mind. Okay. Now, important idea is this. Let's say the initial state, let's say high concentration, low concentration kind of areas are there in the initial state. The final state is when everything becomes uniform. Okay, what I'm trying to say is the concentration profile scenario that we saw, high concentration to low concentration, if that becomes uniform, then the entire material goes to lower Gibbs energy, let's say. In that case, the process is actually driven because we are talking about lower Gibbs energy state as the final state. Gibbs energy also favors this high concentration to low concentration to become uniform. Okay, this is not random jumping alone. There is a Gibbs energy driving there. Because the opposite also is true. Let's say there is a high concentration, low concentration, and if the atom jumps from high concentration to low concentration regime, then the Gibbs energy increases, let's say. If the Gibbs energy increases, the jump is not favored, right? The activation barrier will be really high for that. If that happens, the atoms rather will jump from low concentration to high concentration, because that will reduce the Gibbs energy. Okay, this is called as uphill diffusion. We'll see that. And we will see that not only based on the Gibbs energy change, we will see that based on chemical potential change. That will be more elegant to understand. Let's take this example of copper cobalt at 800 degrees. Copper with 20% cobalt, copper with 10% cobalt. We took 20% nickel and 10% nickel in one of the previous examples where things became uniform, 15% nickel throughout. Right? Here, if you see, so when we join them, this region which has already high cobalt will become even higher in cobalt. This region which has lower cobalt will become even lower in cobalt. Okay, if you bring the concentration profile of cobalt versus distance, initially it was like this, high concentration, low concentration. Then with respect to time, it goes to even higher concentration and even lower concentration. This is the final state. Why it happens? If you only treat it based on the concentration gradient becoming uniform, you will be totally fooled. Right? What you have to figure out is that if the jumping happens and the Gibbs energy is not favoring that jumping, let's say the high concentration to low concentration jumping, if it is not favored by Gibbs energy, the reverse is favored by Gibbs energy, then the reverse only is permitted, because there is a driving for atoms to jump from low to high concentration. Then this will be the result. So instead of concentration, if we talk about chemical potential, let's not talk about Gibbs energy, because chemical potential we can put for each element, right? How is it in its initial state? How is it in the final state for an element? Okay. So if we bring that into picture, chemical potential of cobalt, initial is like this and like this. Chemical potential of cobalt is high here and low here, when the concentration is 20% cobalt and 10% cobalt. Okay. But when it becomes even higher cobalt, even lower cobalt, what happens is chemical potential becomes uniform everywhere. Okay, so this is where Gibbs energy is minimum. Okay, and this is true even for the downhill diffusion. Downhill diffusion is going from high concentration to low concentration, the conventional picture, that's called as downhill diffusion. Even there, if the Gibbs energy drives it, then it will be having this sort of chemical potential curve. Initial chemical potential will be like this: copper 20 nickel, copper 10 nickel, and when they join, they become 15 nickel everywhere. And if you look at the chemical potential of nickel, you will see that initial chemical potentials are different, and when it becomes uniform everywhere, chemical potential also becomes uniform everywhere. So in any case, chemical potential becomes uniform. So let's summarize these ideas together. In terms of concentration, if we write, downhill diffusion removes differences in concentration, uphill diffusion grows differences in concentration. So if you try to understand both of them based on only concentration gradient, you will not be in a position to understand. These things will not be reconciled. Now if you understand them in terms of chemical potential, both downhill and uphill diffusion removes differences in chemical potential. So chemical potential differences are to be removed, and things chemical potential, in the chemical potential sense, it should become uniform everywhere. That means reduction in overall Gibbs energy. And this thing, chemical potential becoming uniform everywhere or Gibbs energy becoming lower, is the driving force for diffusion. Okay. And this picture explains it more elegantly. There are two different cases given here. If you see, there are two materials, one is B rich, this one is A rich. Okay. From B rich side, B atoms are moving to the right. From A rich side, A atoms are moving to the left. This is the downhill diffusion sort of scenario. But in the Gibbs energy landscape, this is how it looks. Okay. This part 2 here is here. This is the Gibbs energy of it. And this first part is here. And this is the Gibbs energy of it. When you just join them, the Gibbs energy of these two pieces together is here. But when interdiffusion happens and things move to equilibrium, the Gibbs energy drops from this value to this value, meaning Gibbs energy decreases for both the sides. That is the reason why this sort of interdiffusion happens. But the opposite can also happen. If you see this, again same 1 and 2, one side is B rich, one side is A rich, but to the B rich side, B atoms come. To the A rich side, A atoms come. So concentration of A keeps on increasing here, concentration of B keeps on increasing here. Why this happens? Because Gibbs energy tells so. You see here, this is the Gibbs energy curve now. Point 2 has this Gibbs energy and 1 has this Gibbs energy. Metal piece 2 has this Gibbs energy, 1 has this Gibbs energy. And then what happens with respect to time, as this kind of uphill diffusion takes place, Gibbs energies decrease for both the sides. From this average Gibbs energy of two metal pieces, it drops to this Gibbs energy value, where we will have two different phases of these two compositions. Okay, so the one with high B becomes even higher in B, the one with low B becomes even lower in B. Okay, that way this Gibbs energy curve tells you the chemical potential becomes equal only when this sort of diffusion happens. That means uphill diffusion happens. So chemical potential we can use to explain this, or Gibbs energy minimization we can use to explain this. Both are fine. And here it is given at these two locations a tangent is drawn. You see, for point 2 here a tangent, and point 1 this here there is a tangent. And if you look at the chemical potentials, what will happen to chemical potential of A and B when it reaches this minimum energy final state, we can draw one tangent like this. And if you see this tangent, what happened to mu A, you see. So mu A was higher here, lower here, and when it reaches final state, it reaches uniform mu A value throughout, not high, not low. Similarly for B also. And in this example, if you see uphill diffusion, this is the initial state Gibbs energy, initial state chemical potentials you can track here. And once it reaches this final state, if you draw a tangent there and see what happened to mu A, mu B, you can see high mu, low mu becomes some average mu, high mu, low mu becomes some average mu. This is what drives the diffusion, right? So when we say diffusion that is driven, our Fick's law was derived with random jump assumption. chemical potential gradient now we know is the one which drives the diffusion in most of the process in solids. If we know this now, we have to incorporate this driving factor into the diffusion equations, right? In order to do that, we will understand diffusion in a slightly different way. That is, in diffusion there is a net flux. Okay, hence there is a net velocity, right? We can say atoms are moving with some velocity. So if that is so, each atom will have velocity v. Then flux can be written like this. Flux is take the concentration, meaning how many atoms are there per unit volume, multiply that with the velocity, you can get number of atoms moving per unit area per unit time. Right? So this is a much simpler way to understand diffusion. And since atoms diffuse to remove differences in chemical potential, we can say the drift velocity is proportional to the chemical potential gradient. Right? So Vb is proportional to chemical potential gradient. And the proportionality constant is going to be mb, and this mb is mobility of B. Based on this, we can write Jb equals mobility multiplied by concentration into chemical potential gradient. So this is much simpler way to understand diffusion and much broader, much more general compared to what we have done in Fick's laws. Okay, so let's compare both of them together. This is with the mobility, this is with the diffusivity. Okay. So for ideal solutions, it can be shown that the diffusivity is equal to mobility multiplied by RT, or mobility equals diffusivity divided by RT. So that is what mobility is. But in ideal solutions, this is fine, where there is no, let's say, the differences in Gibbs energy are not there. Okay. In that way, that is true. But for non-ideal cases, where an atom jumps and it gets trapped there, let's say the driving thing happens, okay, then we have to bring the thermodynamic factor into consideration, multiply that with the mobility part, then you can get the diffusivity. So in a general sense, if you see, when the diffusion is driven, you can still see the concentration profile, calculate the flux and figure out what is the diffusivity. That can be done, but you don't know whether this diffusivity carries the thermodynamic factor part or not. In the ideal case, the thermodynamic factor will not be there, but in the non-ideal case, when the diffusion is driven, there is a thermodynamic factor that you may not be knowing just by measuring the diffusivity. But if you focus on extracting out the mobility from that, then you are basically dismantling the diffusivity into mobility part and the thermodynamic factor. Okay, so you can see here diffusivity has this mobility part and thermodynamic factor. So since we have so much of thermodynamic data, now you can imagine the entire class till the last class was on thermodynamic, computational thermodynamics and applying thermodynamics to materials and understand various stuff. There we have developed Gibbs energy databases itself. So when Gibbs energy databases are available, it means the chemical potentials are available. So from those things, thermodynamic factor can be calculated. And what we need is mobility extra so that we can get the diffusivity. So actual diffusivity is making a database for them and creating the simulations based on that diffusivity, solving Fick's laws and all can happen. But the database becomes too difficult to make if we want to make it only using diffusivity. There mobility becomes a very handy thing. So that's what we will be seeing in the next class. Let's continue with this now. Thermodynamic factor is related to the driving force. Now you understand this already. So mobility for multi-component systems, there is one more idea, Onsager formalism. What it tells you is essentially the similar equation that we saw in the previous slide. Chemical potential gradient is given multiplied by one factor, and this is looking like mobility multiplied by concentration thing here. And then this Jk is flux of the element, this Jk, and Lki prime as a transport coefficients related to mobility. Essentially this part, as I told, contains the mobility, but for multi-components this becomes more complex thing. Mu I is chemical potential, so all chemical potentials come here. So things are in plural here, basically because it is multi-component system. This is written in a subscript notation, so there will be more terms in that. But the core structure you understand, that there is a mobility term multiplied by the chemical potential term, which is the thermodynamic factor term. So these two things go there in Jk. And this is quite useful for multi-component systems. We'll see that in the next class. Thank you. I hope the lecture is useful. See you in the next class.